Hey guys, this video is on molecular orbital theory. First we're going to talk about paramagnetism and diamagnetism. A diamagnetic atom or molecule has all of its electrons paired up, and a paramagnetic atom or molecule has at least one unpaired electron. Now, paramagnetic atoms or molecules behave differently in an external magnetic field than diamagnetic atoms or molecules do. And to illustrate this, there's a couple of examples here. First, this is a schematic over here of what's called a Gauge balance. And what this does, actually what this is able to do, is it's able to figure out how many unpaired electrons there are in a sample. Now, if you remember, back when we were talking about Schrodinger's equation and quantum numbers, we talked a little bit about how electrons behave as if they're spinning, thus the spin quantum number. And what that means is if an electric charge is spinning, it creates a magnetic field perpendicular to the direction of that spin. So spin up or spin down has a magnetic field pointing up or down. So if you have two electrons that are spinning in opposite directions in the same orbital, that effect cancels out and there is no net magnetic field. But if you have an unpaired electron, there is a net magnetic field because there's nothing to cancel out that magnetic field created by that, quote, spinning electron. And so if you put a paramagnetic species, atom or molecule, into an external magnetic field, all of the electrons that are unpaired, their magnetic fields will line up with the external magnetic field, and it will be attracted to the poles of the magnet. So it pretty much stays there and its weight decreases. So what you do with the Gauge balance is you weigh the sample before you turn on the magnetic field and after, and we're able to calculate by the difference how many unpaired electrons there are. Now, this picture over here, it's pretty cool. This is what really happens. The bottom picture here is liquid nitrogen, so N2. You pour nitrogen between the poles of a pretty strong electromagnet and it just goes right through because it ends up nitrogen is diamagnetic. But oxygen, liquid oxygen, on the other hand, does not go through. It gets stuck right in there. So that must mean there's no doubt that this experiment proves that the oxygen molecule is paramagnetic. The problem, guys, is all of our theories up to this point, valence bond theory, hybridization theory, pretty much, predict the oxygen molecule to be diamagnetic. If you draw a Lewis structure of it, all the dots are paired up. There are no unpaired electrons. If you use hybridization theory, you end up with each oxygen being sp2 hybridized, one unpaired electron in an sp2 hybrid orbital, one in a 2p orbital. But when it combines with another oxygen to form the molecule, the 2p orbital has two electrons in it because that's the pi bond here, and the sp2 orbitals also have two electrons in them because that's the sigma part of the pi bond, one electron from each. So there are no electrons predicted to be unpaired in the oxygen molecule with either valence bond or Lewis theory or hybridization theory. Well, obviously there's something wrong with these theories because the experiment shows that it is definitely a paramagnetic molecule. So that means, guess what? We need a new theory. That's molecular orbital theory, or MO theory for short. And what the basic idea, guys, with MO theory is that just like in hybridization theory, where we combine the orbitals on atoms to form atomic orbitals that are hybridized, sp, sp2, sp3, and so on, what molecular orbital theory does is a similar thing, but it takes the atomic orbitals from all the atoms in the molecule and combines them to form orbitals that are spread out over the entire molecule. They're not localized on atoms like they are in hybridization theory, but they're spread out over the entire molecule. And just to remind you, when we say combine orbitals, we're really saying we're adding or subtracting them. And we're not going to do the math. We get to just look at pictures. But what happens is, remember, electrons act as waves, and this is them exhibiting some of their wave-like behavior. And if you remember, waves combine either constructively or destructively. So if two waves combine constructively, their peaks and their troughs line up, and the resulting wave has higher peaks and higher troughs, a larger amplitude. But if two waves combine destructively, where the peaks and the troughs line up, they cancel out and you get, zero, nothing. Well, that's exactly what's going on here with these molecular orbitals. So we're going to start out pretty simple, and we're going to stay pretty simple, really. So what we're showing here is two s atomic orbitals, one from each atom, so a blue atom and a red atom, two hydrogen atoms, let's say, are combining. And when they do, they make, like this, they combine constructively and destructively. When they combine constructively, the amplitude of the wave functions increases. What that ends up meaning, guys, is that there's a greater probability that the electron density is between the two nuclei. And that is a stabilizing factor, and that lowers the energy of the resulting orbital, called a bonding molecular orbital. In this case, because these are s orbitals combining, this is what we call a sigma s bonding orbital. However, when they combine destructively, what happens is the wave functions cancel each other out, and now that region in between those two nuclei has no electron density in it, and so the two nuclei with their positive charges repel each other, and that increases the energy, makes it less stable. When that happens, that's what we call an anti-bonding orbital. In this case, a sigma s anti-bonding orbital. You see that asterisk right there? That means anti-bonding. So the anti-bonding molecular orbital is higher in energy than the individual atomic orbitals, but the bonding molecular orbital is lower in energy than the individual atomic orbitals. One other thing to point out about this is that the number of atomic orbitals we start with, in this case 2, is always equal to the number of molecular orbitals that we end up with, 2, an anti-bonding and a bonding. When p orbitals combine, they can form anti-bonding and bonding, both sigma and pi orbitals. So the top picture is sigma p orbitals forming. So if you get two, so this is an orbital from one atom, a p orbital. This is a p orbital from another atom. If they combine destructively, then they have destructive interference, and they look something like this. Then this is an energy here. This is kind of backwards, but these are higher in energy than when they combine constructively, and you get a bonding molecular orbital, a sigma p bonding orbital, and this sigma p anti-bonding orbital. Again, the asterisk means anti-bonding. Now, in these orbitals, there's this region here, right, where there's no electron density. This is called a node. And when a node is between two nuclei, it increases the energy, decreases the stability of an electron being in that orbital. We can also get pi p bonding and anti-bonding molecular orbitals. And if the orbitals combine constructively sideways, then we get we get two pi bonding molecular orbitals. And if they combine destructively, we get two pi anti-bonding molecular orbitals. We're going to tie all this together in a minute, guys, don't worry. So this is called a molecular orbital energy level diagram, particularly the middle part, the part that looks orange. What we're going to start out doing, and we're going to get away from this pretty quickly, is we're going to show the atomic orbitals from each atom. So this is what happens when two hydrogen atoms combine and we form a molecular orbital in the resulting hydrogen molecule, H2. So hydrogen, a neutral hydrogen atom has one electron and it's in a 1s orbital. So if we take the 1s orbital from this atom, 1s orbital from this atom, combine them, we get constructive interference, a bonding sigma 1s orbital, and we get an anti-bonding sigma 1s anti-bonding molecular orbital. And what we do is we take the electrons that are in the atomic orbitals and fill in the molecular orbitals that form using the same rules that we did before. So we have two electrons here, we end up with two here. In this case, they both end up in the bonding molecular orbital. Okay, so this is just kind of introducing you guys to molecular orbital energy level diagrams. And so this is just a reflection, or just another way of showing really this kind of picture right here. So in this picture, in this energy level diagram, energy increases up. So these are the energy of the atomic orbitals is higher than the bonding molecular orbital, but lower than the anti-bonding molecular orbital. And this is for diberyllium, Be2, right? Same idea. Now, beryllium's electron configuration is 1s2, 2s2. But the valence electrons are the 2s electrons. When we're writing molecular orbital energy level diagrams, we ignore all of the core electrons because their effects, any effects they have, all cancel each other out. We only care about the valence electrons because remember, valence electrons are where the chemistry happens. All right, so a beryllium atom has 2 valence electrons in its 2s orbital. So we have 2 beryllium atoms, 4 electrons. So when we put them into the molecular orbitals, 2 go into the bonding molecular orbital. And then it's full. So now we put the other 2 in the anti-bonding molecular orbital, just like that. So we're not going to go any farther, guys, than second row homonuclear diatomic molecules. So second row of the periodic table, lithium through neon. Homonuclear, meaning both atoms in the molecule are the same. And diatomic, of course, is 2 atoms. So memorize or write on your card these 2 different energy level diagrams. The one on the left, the white one, this is what you use if the molecules are lithium through nitrogen. That's going left to right in the periodic table. But when we hit oxygen, the order changes just a little bit. The only thing that changes, guys, is this sigma 2p molecular orbital now is lower in energy than the pi 2p's where it was higher before. That's due to something called sp mixing, which we'll talk about in just a second. But these are important to remember because this is how you do molecular orbital theory at this level. Is you basically fill these in. That's all there is to it, really. So let's just look at this real quickly. This is showing relative energies of the molecular orbitals for lithium, dilithium through dineon. And what's happening as you go from lithium over to neon is that you get the sigma 2px, 2p molecular orbital goes down in energy. And really what's happening is you can think about it going the other way, going up. So once we hit nitrogen, go over to oxygen, this is where the sigma 2p molecular orbital is lower in energy than the pi 2p's right here. That's why we have the 2 different diagrams. Notice that the difference between the sigma 2s and the pi 2p's gets bigger as we go from lithium over to neon. That's going to be important here in just a second. So sp mixing. So this is an explanation, guys, of why we get that flip between the sigma 2p and the pi 2p molecular orbitals. So the sigma s and the sigma p orbitals, if they're close enough in energy, they interact, they mix together, and the result of that is that the sigma p molecular orbital goes up in energy, sigma s goes down, and so it ends up for lithium through nitrogen, the sigma p and the sigma s molecular orbitals are close enough in energy so that they can mix, and the sigma p molecular orbital ends up being higher in energy than the pi p molecular orbitals. But once we hit oxygen, then these the energies are too far apart for mixing, and now the sigma 2p does not go up higher, but it stays down lower than the pi 2p's. Anyway, that's just an explanation of why the order changes. But really, as a practical matter, you just need to know the 2 diagrams. So let's do some examples. So if we look at the diborane cation, so B2 with a plus charge, we want to fill in the molecular orbital energy level diagram. So because this is, before oxygen, we use this one, the one where the sigma 2p is higher than the pi 2p's. This molecule has 5 valence electrons. That, guys, is important to make sure you count the right number of valence electrons. So each boron has 3 valence electrons, times 2 is 6. The plus charge means we lost one, so there are 5. We just fill in these orbitals, guys, just like we did with atomic orbitals, following exactly the same rules. Aufbau principle, Hund's rule, and the Pauli exclusion rule. So 5 electrons, okay, we can only put 2 in each. If they're in the same orbital, they have to have opposite spins. And when we get to degenerate orbitals, 1 goes in each, all with the same spin before we pair any up. So 1, 2, 3, 4, 5. Now, okay, this is kind of awkward to typeset. So we have an alternate way of writing this exact same thing, and that's this right here. This is another way of writing this molecular orbital energy level diagram. Sigma 2s2, that represents this right here. Sigma star 2s2, that's this antibonding orbital. And pi 2p1, there's 1 electron in this. So the superscripts say how many electrons are in those orbitals, and this just tells you which orbitals we're talking about. And energy goes from left to right, just like it goes from bottom to top in this way of writing it. So for O2 minus, the oxygen anion, molecular oxygen anion, we have 13 valence electrons. 6 from each oxygen times 2 is 12, plus 1 for the negative charge is 13. So we start at the bottom, alphabet principle, no more than 2 each, the Paul exclusion rule, 2, 4, 6. When we get here, put 1 here, 1 here, that's Hund's rule, 8, 10, 2, 4, 6, 8, 10, 11, 12, 13. Or if we write it out like this, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, 1, 2, 3, 4, and pi star 2p3, 1, 2, 3. That's really all there is to it, guys. We can, now that we know how to fill in molecular orbital energy level diagrams, we can calculate what's called the bond order. This is the formula right here. It's just, you look at your molecular orbital energy level diagram and you count up how many bonding electrons there are, subtract out antibonding. Remember, antibonding electrons are the ones with the asterisks, right? So bonding minus antibonding over 2 is the bond order. For example, in the boron cation, sigma 2s2, sigma star 2s2, pi 2p2, there are 2 plus 1 is 3 bonding electrons, and 2, because of the asterisk, antibonding electrons. So the bond order is just 3 minus 2 over 2 is 1/2. Now a couple things about bond order, guys. First, the higher a bond order is, the shorter and stronger that bond is. So we can predict relative strengths of bonds. And if we have a bond order of 1, that means basically a single bond. A bond order of 2, a double bond. A bond order of 3 means a triple bond. But we can have half bond orders too. So like for this example here, a bond order of 1/2. Well, what does that mean? It means that, first of all, this molecule is predicted to exist, and that the bond is longer and weaker than a single bond, but it's still there. Now, write this down because this is important too. If when you calculate the bond order, you get a bond order of 0, that means this. Molecular orbital theory predicts that that molecule does not exist. It is too unstable to exist. That's important because that's one thing that molecular orbital theory does for us. It helps us predict whether or not the molecule can exist. So bond order of 0 means the molecule is not predicted to exist by molecular orbital theory. The higher the bond order, the shorter and stronger the bond. We can have half bond orders. So let's work out an example. So we want to find the bond order of this molecule here, dicarbon with a 2 negative charge, and we want to figure out if it's paramagnetic or diamagnetic. So why don't you guys go ahead and figure this out and come on back when you get an answer. Welcome back. So let's see what we got. So C2, 2 minus, there's 4 valence electrons from each carbon. 4 times 2 is 8. The 2 negative charge means we add 2 more, so we have 10 valence electrons. So we fill in, we use, because this is to the left of oxygen, we use the one where the sigma 2p is above the pi 2p's. 2, 4, 6, 8, 10. So the bond order, the bonding electrons are 2, 4, 6, 8. 8 bonding electrons minus 2 antibonding electrons. 6 over 2 is 3. So pretty strong short bond. And because all the electrons are paired up, this is diamagnetic. Now, a good practice for you guys would be to write out the molecular orbital energy level diagram for oxygen, the oxygen molecule, O2, and then you'll see that it is predicted to be paramagnetic by molecular orbital theory, and thus it matches experiment. So it's in this scenario, it works better than hybridization theory. But remember, guys, we have these, well, 3, maybe 4 theories now: Lewis theory, valence bond theory, hybridization theory, and molecular orbital theory. We don't say one is better than the other. Just some situations one works better than the others, and we choose that one. So we get to choose whichever one we want based on which one works better for us. And that's all there is to it, guys.